let's go over the quiz while it's still fresh in your mind. Problem number 1.
Could you put
Let
on
this-
the, could you put on the microphone?
sorry.
Thank you.
I'll repeat that. Let's go over the quiz. Problem number 1 is this one. You have this demand function. U sub d equals this function d for demand. It's a function of price and income. Y sub 0 is income, and y sub 0 is considered an exogenous variable. And you are given that partial d partial p is negative. Basically, that's the law of demand. And you're also given that partial d partial y sub 0 is a greater than 0. In other words, as income goes up, quantity demand goes up. So this is a normal good. That's typically what we'd expect. The supply function is this simple function. U sub s equals s of p. S for supply. Notice quantity supply is just a function of a single variable, p, in this one. And you are to assume that ds dp is positive. Now, that's the law of supply. As price goes up, producers want to produce more. Under what conditions can you express the equilibrium price, P star, as a function of income? Well, let's rewrite this. Notice the equilibrium condition, which I did write on here. But the equilibrium condition, of course, is QD equals QS. Or alternatively, it's QD minus QS equals 0. The equilibrium conditions can always be written this way, equals 0 form. So can the first order conditions in an optimization problem. So we can rewrite the equilibrium condition this way. F, capital F is a function of P and y sub 0. Those are the two variables here. Not including quantity. But in equilibrium, QD equals QS, so that disappears, okay? So we can express our equilibrium condition this way. Write quantity demanded using this function minus quantity supplied, which is just S of P, equals 0. You can see in the right-hand side, there's just two variables, P and Y. So we've got it in this form right here. So now we want to know, and actually I could rewrite this way. In equilibrium, if this condition is satisfied, this will be P star. So we want to know under what conditions can we write P star as a function of y sub 0. So it's a perfect setup for the implicit function here we were discussing yesterday. Now what you require is this. 1, you require that f sub P star, or f sub P, and f sub y 0 be continuous functions. So let's just assume that they are. Okay, we'll just assume that they're continuous functions. That's a pretty innocent assumption. Furthermore, let's assume that there exists a price and an income value that satisfies that equation. Then all we need is the second assumption is f of P star does not equal 0. And actually, let's find out what f of p star is. Notice f of p star is just this. It's partial d, partial p star, minus ds, dp star. But by assumption, this is negative, the law of domain. By assumption, this ds dp is positive, so you've got a minus sign in front of it. So the partial derivative of capital F with respect to p star is always negative. By assuming that the domain is downward sloping, supply is upward. So therefore, we can conclude that this function does exist. We can find a neighborhood around y sub 0 in which p is a function of y sub 0. And by the implicit function theorem, dp star dy0 is just this. It's minus f y sub 0 subscript over f of p star. And f of y sub 0, if you go back to this equation, is just this. Put our minus sign in there. F of y sub 0 is just partial d, partial y sub 0. F of p star, we just found that by substituting down here. We just found out this was negative. You've got a minus sign here, so that then it becomes positive. Partial d, partial y sub 0, by assumption is positive. So you've got a negative, negative, positive. So the sign of this derivative is positive, which makes sense. Because as income goes up, what happens to the domain curve? You think of supply and demand diagrams. If you think of supply and demand, here's the price, here's quantity. The domain curve is downward sloping. We don't know what its shape is, but it's always downward sloping. The supply curve is always upward sloping. Where they intersect, that's where your equilibrium price is. Now, as income goes up, what happens to that domain curve? Shifts to the right. And if it shifts to the right, the equilibrium price is going to rise. So this answer makes intuitive sense. Anytime there's an increase in income, it should cause the equilibrium price to rise. Actually, we discussed this earlier in the context of the linear supply and demand model. We got that same result. That vertical intercept A were to go up, perhaps because of increase in income, you get a rise in the equilibrium price. You could show that mathematically. But this is a more general result because, see, we're not making any assumptions about the functional form of demand and supply, other than the signs of these partial derivatives. That's the only restriction we're requiring now. So it's a more general result. Okay. Any questions on that? If you didn't get this completely right, this is the first example that Chang discusses in the section on the use of the implicit function theorem in economic models. So it's right in the textbook if you need to review it. Okay. Number 2, on the basis of Taylor's formula with the Lagrange form of the remainder, what we just call R sub n in class, show that at the point of expansion, x equals x of 0, the Taylor series will always give exactly the value of the function at that point. This is very easy to prove. If you just write down the formula, you can see that this has to be true. Let me rewrite Taylor's formula. Phi of x is equal to phi evaluated at x of 0. That's a specific value of x, called the point of expansion. Plus the second term is going to be phi prime of x evaluated at x of 0 times x minus x of 0. You could put a 1 factorial down here, but that's just 1, so I'm going to omit that. Plus the next term would be phi double prime evaluated at x of 0 times x minus x of 0 quantity squared. And let me, I could just put 2 here, but let me put 2 factorial. 2 factorial is 2, so you could just write it as 2 if you wanted to. Plus, what would be the next term? Let's just do one more. What would be the third term in Taylor series?
R to the third, x of 0.
Okay, phi
To the third.
third, yes, okay. Okay, and let me write that as just phi triple prime. No ombrion,
Times x minus x of O to the third
right?
over 3 factorial.
Right, over 3 factorial. Okay. Now, I'm just going to put the rest of them, they follow in a similar sequence. Until we get to the last one, and that would be what? Phi raised to the what power?
Yeah.
N. I'm sorry, I shouldn't say phi raised to the nth power. This is the nth derivative of phi. Okay, so we phi superscript parentheses n times x minus x of 0 raised to the nth power all over n factorial. And I'll put a bracket here, like the book does. This is the polynomial part. Then you have your remainder term, r sub n, which is just this, phi. And the order of the derivative, that's the way we should say it, is what?
N plus 1.
N plus 1, right? So it just follows in sequence. Evaluated, is that at?
X minus,
No. P.
Yeah, P.
Yes, you were asking about that earlier. Now, we don't know what P is. We know it's some value between x, whatever x is, and x of 0. Okay. But this is the undetermined part. Over n plus 1 factorial times x minus x of 0 raised to the n plus 1 power. Okay, that's the remainder. Now, suppose x is equal to x of 0. So what would Taylor's theorem simplify to? Suppose x could be anything. Let x be x of 0. So you're evaluating phi at x of 0. Then what happens to this Taylor's formula?
Everything cancels out except psi.
Yes.
X of 0.
Yes, because x minus x of 0 then, Zach, is what?
0.
0. So that's a 0, that's a 0, that's a 0, that's a 0, and that's a 0. So all of these terms drop out, and this formula then becomes phi of x of 0 equals phi at x of 0, which is comforting. So you know, let me just generalize this a little bit. If x is not too far away from x of 0, then the Taylor's approximation is going to work pretty well. You can see that if it's exactly x at x of 0, then Taylor's formula gives you exactly the right answer. Yes, that one.
Like, it's just being nitpicky, but since the camera line, isn't that supposed to be the derivative of phi to x sub 0, or the derivative of phi x sub 0?
Okay, say that again.
Right, no, to the left,
Left.
yeah. Aren't you?
Oh,
Yeah, just
yes,
'cause the
I
camera's
should.
on.
Yes, I should have a parentheses x of 0, thank you. Is this derivative, this nth derivative, is evaluated at x of 0? Yes, thank you. Okay. So more generally, just realize that Taylor's approximation is going to work better the closer x is to x of 0. You can see if x minus x of 0, suppose this is a fraction, then you're raising a fraction to the n plus 1 power, so this will be going to 0 if it is big. On the other hand, if x is very far away from x of 0, very far away, then this term right here, x minus x of 0 to the n plus 1 power, could be quite large. So possibly could cause problems. However, you are dividing by n plus 1 factorial down here. That should help. And hopefully, if you do enough derivatives, hopefully the derivatives will vanish or be 0 or be very small, in which case this term will be small. All right, any questions on that? Okay. Problem number 3. By the way, this problem I took right out of the book. Problem number 3 is this. Suppose you have y. Notice y is a function of x. I'll just insert that so that wasn't introduced. Equals 100 minus x minus 5 raised to the 4th power. Find the stationary values of y. That would be the values of y where the first derivative is 0. It's called the stationary value. Stationary value could be a maximum, could be a minimum, could be an inflection point. So you want to find the max or the min, or the inflection point. Take dy dx, or f prime of x, let's call it f prime of x. Take the first derivative, notice the first derivative, minus 4, x minus 5 to the 3rd power. Set this equal to 0. It's obvious the only way this is going to be 0 is if this term within parentheses is 0. So the critical value of x is 5. Okay. Now, let's take the second derivative, f double prime of x. F double prime of x is just minus 12 x minus 5 squared. Now, you evaluate this second derivative, the critical value of x. So if we look at the value of the second derivative, the critical value, we get 12, 5 minus 5 is 0, so this is 0. So this is kind of a problem case. You know, if that second derivative is negative, we would have a what? No, a max. If the second derivative were positive at the critical value of x, we would have a min. Okay. So in this case, we don't know. We have to do further checking. We have to use the nth derivative test. So you just keep differentiating. Get the third derivative with respect to x, and it's going to be minus 24 x minus 5 to the 1 power. But at x equals 5, this is also 0. So the third derivative at x equals 5 is 0. Now, Brianna had this third derivative at the critical value of x not been 0,
Then we had either max or min.
nope, had it not been 0, you would have had
Oh, and inflection.
an inflection point. See if the first non-zero derivative is of an odd order, that indicates an inflection point. But in this case, it's 0. So we've got to go on to the fourth derivative. And the fourth derivative, notice, is just what?
24.
Minus 24. Minus 24. So the first non-zero derivative is of order even, is fourth. And it's negative, so what do you have at x equals 5? The maximum. So this implies that f of 5 is a maximum. And actually, this nth derivative test is, as the book explains, is derived in a pretty straightforward way by using Taylor's theorem. Actually, how could you figure that out intuitively? By the way, what is f of 5? What is the maximum? 100. Because see, at x equals 5, this term drops out, but you do have this constant. So the maximum is f of 100. Why is that intuitively obvious that that is the maximum?
You can see that the negative function there, x minus 5 to the fourth is a parabola. And it's an upside down parabola because of the minus sign.
Okay. Or put another way, what is x minus 5 raised to the fourth power always going to be? Just paraphrasing what you're saying. This term right here is always going to be what? Positive. Could be 0. At x equals 5, it's going to be 0. But at any value other than 5, this term here is going to be positive because you're raising it to the fourth power. Because see, if this were a negative number raised to the fourth power, that would be positive. This is a positive number raised to the fourth power, that's positive. And you're subtracting something from 100. So the maximum has to be at x equals 5 because that'll make it 0. So you won't be subtracting anything. So intuitively, you know the maximum is 100. And this is, of course, going to be a global maximum, not just a relative maximum. It'll be a global maximum. Okay. And if you graph this, Zach, you would see that you do indeed have a maximum of 100. Right? Because it'll be, if you graph this function, it'll be upside down u with a maximum right there. Okay. Okay. In our remaining time today, what we are going to do is basically chapter 10 in the textbook. And that is exponential and logarithmic functions. Okay. An exponential function could be written in this form. And let our right-hand side variable be t, little t rather than x. The reason for that is a lot of times in exponential problems, the independent variable is time. So that's why we're using a t rather than x. You could use x, that's okay, but Chang uses t, so I'll just follow him in this regard. So suppose y is some function of t, and just let it be this simple function, b raised to the t power. Notice the independent variable t appears as an exponent. This t, the independent variable, appears as an exponent. So that's why it's called an exponential function. B, the term b, is referred to as the base. You're raising the base to the t power. By convention, we let b be some number greater than 1. Okay. So that's the only restriction on b. We do want it to be positive and some number greater than 1. But that's the only restriction. So let me give you a simple example. Suppose we have this function, y equals 2 raised to the t power. Now the base b is equal to 2. And if we were to graph this function, it looks like this. Let's calculate the value of y for different values of t. Let's start actually with negative values of t. There's no restriction on t here. So suppose t is minus 2. Then what would y be?
1/4.
Okay. 2 to the minus 2, just a little refresher on algebra. If you have y equals 2 to the minus 2 power, then this would be the same as 1 over 2 squared, or 1/4. Okay. So y would be 1/4. So we would be right here, t equals minus 2, let's say it's right here. And then, let's say this is 1. So 1/4 would be about right here. Suppose t is minus 1, then what will y be? 1/2. 2 to the minus 1 is 1 over 2, or 1/2. So at the minus 1, how about t to the 0?
1.
Yes. 2 raised to the 0 power, any number raised to the 0 power is going to be 1. So this will be a 1 here. So this would be this point right here. Okay. T equals, we did 0. Okay, so t equals 1. 2. 2 to the 1 power is going to be 2. Okay. And that one would be up here. And t equals 2, that's the last one we'll do. 4. Notice what happens every time t increases by 1. Oh, we're going to stop there. What does y do? Yeah, every time t increases by 1, the value of y doubles. So, for very large values of t, of course, the values of y will get very large. Because every time you increase it by 1 unit, it doubles. So the graph of this would look like this. That would be the general shape of an exponential function. What if I changed it to this? What if I looked at this, y equals 2 to the minus t? What would happen? If I raise it to the minus t power rather than t, what would the shape of this curve look like? This is y equals 2 to the t.
Would be very large for negative values of t.
Yes. In fact, it would be just the mirror image of this. Come down like this. So this is what y equals 2 to a minus t. Just be the mirror image of that. Okay. Another modification we could make would be consider a function like this. Y equals c times b to the t, where c is some non-zero constant. If c were positive, then all this would do is it would move up this curve by whatever the factor c is. For example, if c were 2, the height of this would just be double for any value of t. Okay. So this would also be an exponential function. Now, it's convenient in dealing with exponential functions to deal with natural exponential functions. And a natural exponential function has this form. We let the base be the mathematical constant e. And so if you're dealing with this type of equation, this is a natural exponential. And let's talk about this number e. Very fascinating number. You know, on first glance, there's nothing natural about this. But when you look at it, what E is. E is an irrational number. That means it's a number that has a non-repeating, non-terminating decimal portion. So do any of you know approximately what E is? Actually, you should all have calculators. Well, actually, I didn't bring mine with me. But for the first 5 digits, to the first 5 digits, what is E?
2.71828.
2.71828.